at number number 8. And I've got okay. You remember there are 5 basic types of reaction. There's single replacement, double replacement, decomposition, combustion, and combination. So if I were to look at this, what's going on here? From the reactants to the products. Remember, reactants, products. What's actually happening? The oxygen is taking place of the sulfur. So we've got an anion replacing an anion. So while it doesn't really look like it, this is just a single replacement. Okay. If we had a reaction like number 2, we got something like this going on. We've got cation, anion, cation, anion. This is where you get 2 couples going out to the swingers bar, and they go home with each other's other. So the sodium cation has said sayonara to the phosphate and hooked up with chlorine. And hydrogen and the phosphate are hooking up, so this is a double replacement. Okay. If we have combination, that's pretty much a standard. You've got, let's see what would be an example of a combination as well. I have one on here. Combination will be something like barium plus sulfate producing EaSO4. Yeah, okay. So that's just a combination. I'm taking an anion and a cation and I'm putting them together. Then I can have the reverse of that, which is decomposition. So if I've got barium sulfate, and it's breaking down into its 2 components, that's a decomp. And then combustion, that's basically any time you have something combined with oxygen. Basically any time you burn something. Okay. So remember those 5 types. So when we're looking at the lab this afternoon, we'll be looking at what kind of types of reactions we have. But we're also going to be looking at, do they produce, I thought you had a question, sorry. I thought you said something. You made a derogatory comment about lab, didn't you? Okay.
Technically Monday.
Do what?
It's technically Monday.
Yeah, it is. Tell me about it. We didn't get in until late last night, and then we had a text message about, we're having a birthday party at Elvacare. Oh, crap.
Yes.
All right, so we've got the 5 different types of reactions. But these can also be other types of reactions. We can have exothermic and endothermic reactions. You guys remember what those are? Anybody out there?
Heat is released.
Yeah. Or absorbed. So, one of the things we're going to look at in the lab today is we're going to have an endothermic, we're going to have an exothermic. Depending on which kind you are, your heat will either be a product or a reactant. So, I'll give you the answers to the first. So, for instance, on question A-3, where it says add heat, one of these will generate heat when you mix the two together. One of them will give heat off. One of them will generate heat. One of them will become cold, which means it's absorbing heat. If it becomes cold, that is an endothermic reaction. And it would be written with heat as a reactant. So it would be A plus B plus heat yields AB. If you go to the drugstore, if you've got like a muscle sprain or something like that, have you ever gotten one of the packs that you can break and it becomes cold? That's an endothermic reaction. I wish to God I'd been the one to think of that. But that's an endothermic reaction. That's basically, well, the ones that produce heat are sodium sulfate, no, sodium acetate in a bag. That's all it is. Oh, if I could have thought of that. Y'all have a different chemistry teacher. All right, so then, if we've got an exothermic reaction, it's going to become hot. It's giving off heat, so heat is a product. So you'll have A plus B yields AB plus heat. Wash.
Thank you.
Yeah, y'all be careful. There's apparently a nasty cold starting to go around.
What?
Yeah. Well, of course, it's the first time we've all been back together after a month. Okay, questions about that? So, one of these, A.3, will give off heat when you put it together, and you'll be able to feel it. And the other one will become cold, and you'll be able to feel that too. All right. So, when we have these reactions going on, there's different things that we can do to speed them up. For instance, if I am an So what kind of reaction is this? It's two different kinds. Endothermic and a combination. Or a combination which is endothermic. All right, so my reaction's chugging along. Basically, when you have chemical reactions, they follow a standard curve. You've got when you first started mixing your product, your reaction, your reactants, and all of a sudden the reaction will take off. You'll hit the peak, and then you'll fall off, and here are your reactants. Okay. These will go at different speeds, and there are things that you can do to affect them. For instance, if I'm an endothermic reaction, and I'm trying to get rid, or I'm trying to absorb all the heat I can, if I add more heat to it, that reaction will speed up. This would be a sharper curve. It likes heat, it wants heat. You give it more heat, it's going to go faster. When we have reactions going on, basically, remember, we've got all these particles swimming around in solutions. Morning. Everything okay?
Yes.
you've got all these particles swimming around in this solution, typically. And you've got to have enough energy to make them hit. But you don't want so much that they bounce off each other. You don't want so little that they never really hit. And then they've got to be lined up correctly. If I try to take two molecules and react them together and they're shaped like that, they're just not going to go together no matter what. But if they're turned, they can react. It's amazing in the first place that chemical reactions ever take place. It really is. But think of how many that go on all day long, just in your one body. So, I'm sorry, I was taking a trip without leaving the farm, talking about chemical reactions. So, if I'm an endothermic reaction and I add heat to it, I'm going to speed up the rate of collision. So my reaction is going to go faster. If in turn I'm an exothermic and I add heat, it's trying to get rid of heat, so it's going to slow down. You're putting something there that it doesn't want. If I'm an exothermic reaction and I cool it down, it's going to go faster because you're helping it get rid of heat by cooling it down. Make sense? So, if we've got reactions, there's basically four things we can do to change the rate at which they go, right? Which is called the reaction rate. We can change the nature of the reactants. All right. Basically, if I try to take methanol and water, methanol isn't soluble in water. It doesn't really matter what I do to it. I'm usually not going to make that methanol go into the water. But if I change my alcohol from methanol to ethanol, it goes right in. Ethanol is soluble in water. We see that every day. Every night when I get home, we're having my scotch and wine now. Okay, so we've just changed. It's still an alcohol. It's just a difference of the number of carbons on the chain. All right. We can change the nature. We can change the concentration. If I use 1 mole of A and 1 mole of B, I'm going to get one rate. If I double it to 2 moles of each, it's going to go faster simply because of the sheer number. There's more molecules mean more collisions. More collisions mean more reaction. Okay? We can change the temperature. Endothermic, exothermic. Most actually, unless it's an exothermic reaction, most chemical reactions will go faster with heat simply because the heat is making the molecules move faster. So the faster the molecules move, the more likely they are to collide, the more number of collisions.
Does that mean more reactions are endothermic than are exothermic?
Probably, yeah. Or that they don't give off any temperature change at all. But still, just the physics of increasing the temperature, increasing the speed at which the molecules move. Because remember, that's how we go through phase changes, by increasing temperature, or energy applied to the system. The last one is catalyst. Catalyst is something that you add to a reaction that creates an environment for the reaction to happen. So it's the wine and the flowers and the chocolate of the first date. All right. It doesn't really enter into the reaction. It'll go in, you can get it right back out. But it'll increase the speed at which if the reaction's going to go, you put a catalyst in there, it's going to increase the speed at which the reaction happens. To the point, I think I've told most of you guys the story about the catalyst, the plant that I worked in that took out the plant. Yeah. it increased that reaction big time, like $1 million worth of renovation, big time. So, fortunately, nobody was good. Did you guys see the Italian cruise ship that bit the dust? How about that GPS?
What happened? I didn't even.
This ship, it was like a $58 million ship to build. It was 3 years old, had 4,000 people on board. It hit a rock in shallow water and went over, keeled over.
Like right while we were eating and everything in the middle of the day.
Yeah.
There's
But you would think the GPS would have seen rock.
Yeah.
So, and now the captain's in jail because he left the ship before all the passengers. Matter of fact, they haven't found everybody yet. There's 6 people confirmed in now, 20 still missing. About 18 miles offshore. What did 18? I think it was 18 miles offshore, off the coast of a little island in Italy. See, yes, technology, but we need to know how to use it. All right. So we've got those reaction rates going on. If we want them to go faster, there are things we can do to make them go faster. If we want them to go slower, there are things we can do to make them go slower. One of the things in the lab that we're also going to be looking at, all the pages of the lab, is shifts in equilibrium. And we really haven't gone over that. Did we go over that in Chem 1? Okay. I know we did, but I know it's been a while. So, basically, there is a dude named Le Chatelier. And he came up with the idea that reactions, even though we tend to think of them as going one way, for instance, all the reactions on the balancing equation sheet that we did, the arrows all went like this. You had maybe AB plus CD yields AD and CB. Double replacement reaction. And we're looking at the arrow, and everything we've seen so far, the yields arrow goes that way. However, in reality, these equations can reverse. You can get to the point where you've used your reactants, you've made your products. If you let it keep reacting and don't stop it, it'll actually reverse back the other way. And you'll get to a point where you have as much product and as much reactant existing on both sides. You've reached what's called equilibrium. My products are making reactants, my reactants are making products. They're reversing back and seesawing back and forth. Right? If you're selling these things, or if you need these things in your next reaction or in your lab to do something, you don't want that to happen. You want to kill the reaction before it gets to equilibrium. The way you know whether it's reached equilibrium or not, there's a calculation, it's called KEQ, and it's the concentration of the products divided by the concentration of the reactants. If, when we were balancing this equation, we had to say 3 of these to balance out 2 of these, I know that's not really balanced, but just pretend, then the coefficients become powers. You have AD squared and then CD cubed. Now, of course, you'd have to know what the concentrations are that you're putting in, and usually when you're running a reaction, you do, or things can go boom. But this in general is the KEQ. Look at another way.
equal 1?
No. It will equal whatever. And what you do when you calculate this before the reaction, it tells you at what point, say you're measuring the concentration. So at what point your concentration has to be of your compound. For instance, say we've got this crank along and say we calculated that the KEQ, the point of where reaction is going to be equivalent, meaning this is seesawing back and forth and equaling each other. If we say it's 2 moles, right, and we're measuring the concentration, we would actually measure it throughout the reaction. And we would know we don't want it to get to 2 because we don't want it to hit equilibrium, but we want it to get as close to 2 as possible.
How come?
Because you want the most of this. If you're running the reaction to make these two things, you want to get maximum product, but not to the point where you're going to start flipping back to reactants. So you know at a concentration of 2 moles, you're going to be at equilibrium. So you cut it off, you do whatever you can to kill the reaction. For instance, if it's an exothermic reaction, it's giving off heat, I might heat it up to make it stop. Okay? So the number, what the number is will depend on what your concentrations are. All right. Now, the dude with shot that I was just talking about said, well, okay, we're not perfect. Sometimes we flip into equilibrium and we don't want to, but we didn't catch the KEQ in time. Yeah, there's a page missing, so I'll bring it in. We're having copier issues and printer issues, and I think whatever they're doing in 603 to turn that into the whatever they're doing to it, they snipped some wires somewhere because there are several of us that were disconnected from the printer. Okay, so Le Chatelet said, all right, we made a boo-boo, we're at equilibrium. We don't want to be there. So there are things that we can do. There are stresses we can add to the system. All right, that's exactly how he turned it, stresses. All right, because a system in equilibrium, that's where nature wants it to be, in reality. That's putting forth the least amount of energy. Everything's just kind of seesawing back and forth. Nobody's bitching, nobody's complaining, everybody's happy, there's no energy there's minimal energy. But what we can do is apply these stresses to the system and make it shift one way or the other, depending on what we want it to do. All right? So if we increase a reaction, let's see abbreviation for reaction or XM component. All right. So if I'm at equilibrium here, and I increase reactants, my equilibrium will shift towards product. All right? So if you increase reactant, it will shift to product. Meaning I've unbalanced it. I've now got an excess of reactants, so of course I'm going to want to start making more product because I want to get back to equilibrium. Or we also term that a shift. If I increase product, well, now I'm going to shift back the other way. I'll shift to reactant or shift left. So if I've got an excess of this, it's going to go that way. If I've got an excess of this, it's going to go that way. And actually, there are times when you want it to go back to your product or to your reactants, because sometimes maybe the product didn't turn out exactly as you wanted it to. But you don't want to waste those reactants, so you shift the product back. We're almost done. I can see you guys look at the clock. Everybody's like, oh, it's torture. All right. So, again, if maybe this was good, but this isn't maybe where you want it to be, so you might want to unwind or unreact it, increase one of these concentrations, and then let it react again. So they told me that would be done today.
I never lied.
All right. So, the second thing we can do, the second stress, let me know if I'm erasing too fast, is we can remove a reaction component. So, all right, here we are at equilibrium, and I remove product. All right, we're seesawing back and forth, and I remove some of this. What do you think is going to happen? If we want to have the same amount of product and reactant, and I've removed product, it's going to shift towards the product. It's going to want to make more because there's an imbalance here. Okay, so if I remove product, it's going to shift to product. Or, there's a missing heat. Or shift right. Because again, it's trying to get everything equal. If I remove reactant, where is it going to shift? Shift left. Towards reactant or left. Whatever it needs to do to restore that balance, it's going to fight you because it wants to be a balance and you don't necessarily want it to be. Okay. Third stress we can add to it is temperature. That works if it's an endothermic or exothermic reaction. So if it's endothermic, where did we say the heat was? On which side of the reaction is the heat? If it's endothermic, product or reactant? Endo.
No.
Reactant. No, it's reactant. You're right. Okay. So heat would be, I'm just going to indicate heat like that, is a reactant. It needs it to react. So if I increase the temperature, what's going to happen to my equilibrium? Okay, think about it. We're at equilibrium. All right. Heat is over here on the reactant side. If I increase reactant, it's going to go towards product. It would be a shift right. So I'm going to increase T. Let me do this. Does that make sense? Does my shorthand make sense?
Is that just increasing heat?
I'm just using heat as this time to represent heat, or triangle to represent heat. Okay, then what about if I decrease my temperature? Shift left. Because I've decreased a reactant, so it's going to shift to try to make more reactant. Does that make sense so far? Okay. If it's exothermic, then heat is a product. So if I increase heat, what have I done? I've increased product, so I'm going to shift to reactants. I'm going to shift left. And then if I decrease heat, that means I've decreased a reactant, so it's going to shift right. Okay? We can increase pressure or change pressure, sorry. Change pressure. And this applies to gases only. Gases are more soluble at increases in pressure. That's why when we bottle beer or soda, they do it under pressure. And what's the first thing that happens when you get that nice psh sound? Because you've changed pressure. You've released the gas. All right? So if you increase pressure, which way have you shifted the reaction? Think of pressure as a reactant.
So you increase pressure?
So if I increase pressure, I've increased the reactant, so I'm going to shift towards product. So shift right. If I decrease pressure, then I've decreased a reactant, so I'm going to shift back towards reactant, towards the left. The last one, anybody want to take a stab at what the last one is? Catalyst. We can add a catalyst. Now normally we don't take catalysts out, we just add them. Adding a catalyst will either shift it towards product, so it'll shift it to the right, or no effect at all. Catalysts only work to a certain extent, just like the wine and the flowers and the chocolate only work to a certain extent. The rest of it's up to you. Okay. Now, all of these really are temporary things. We'll shift the equilibrium, but eventually the system will go back to equilibrium because, again, that's where it wants to be. All right? But if you've got to get the product, if you're selling, if every 1 gram of AD makes you $1 million, you're going to want to sell as much of that as you can. Okay?
Of AD, like your product.
Mm-hmm. Typically when we're running reactions, we're putting two things together to get something different. And remember, that's one of the characteristics of a reaction, is that you can have two independent compounds, put them together, and you're going to come up with something different and completely different. Just like we can take sodium and react it with chlorine. Independently, either of those would kill us. But together, they taste good. And we can eat it. It'll eventually kill us if we eat too much of it, but not like converting into hydrochloric acid in your lungs, which is what chloric gas does, or blowing up with water, which is what sodium does. Still, let's see if we can get some sodium.
So is that why they, with products, they dip it, you know, like after, like an expiration, I guess? I don't know. Is that what they're
Like
saying?
food products you're talking about?
Well, maybe like hair products
Um,
or things like after a certain point. I don't know, do they,
Most of the time, they put those on there to force you to buy more.
so it's not really that the product's gonna go back?
It can. Don't get me wrong, it can. But most of the time, like milk, the expiration date on there is more to protect the producer and to get actually more money, because milk's usually good for about another week past the expiration date. But how many of us pour it out if it's hit the expiration date?
Smell it and drink.
It's too expensive now to pour out after the expiration date. If it smells good, I'm gonna use it. So, but yeah, hair products and things like that. Most of the time, they're pretty stable, and they're really not going to go back the other way in the amount of time it takes for you to use them.
Okay, so this equilibrium could take
It could take months.
months.
It could take years. It depends.
Kind of like fingernail polish, you know, when you buy fingernail polish, they end up getting hard. That's because we've had them, what, a year or two, so it went back to solid.
But if you add acetone to it or nail polish remover,
Yeah, just go back.
it flips the equilibrium.
Okay, so what would it, would it be the acetone be a catalyst?
It's one of the reactants.
Reactant. Okay.
Because it is, I mean, that's a great example, thank you. But the acetone volatilizes.
Okay.
So if you have your nail polish and you've used it, you don't use it very often, but you use it enough, it'll still, the acetone, which is one of the reactants, will
Make more product.
volatilize. And the product, so you've actually moved one of the reactants.
It's like dehydrated, like the vaporized. It's almost like acetone vaporized.
It
Because
does.
we did that in chemistry. That's the only reason why I remember the fingernail polish.
Yeah.
It's almost like it vaporized like water. And so you put in more and it'll loosen it back up from the solid.
That is such a great example. It really is. But it's, yeah. So as the acetone is drying up out of the nail polish, it's going back to its solid form. The dyes and all that kind of stuff that's in there. Then if you add more acetone to it, which is its reactant, then it's going to go back to product.
Okay.
Okay. All right. These are some of the things we're going to be looking at lab today. And seeing whether these things are exothermic and endothermic, if we think they're going to shift to the left, to the right. Are there things we can do? Like, okay, I've got this reaction, it's doing this. If I heat it up, what happens? Well, they go faster. So, any questions about anything? I won't torture you guys. We'll get out of here at 11:45, right? Yeah, I won't torture you the whole time. Let you go take some time to read what lab you do have, and I'll bring the other pages.